Good afternoon, everyone. On behalf of the PALS Program Management Office, it gives me a great pleasure to warmly welcome our dignified resource persons from IBM Research Labs, students and faculty from our partner institutes, and all our PALS champions. We have Mr. S. Krishna Kumar and Mr. Ravi Venkatraman here with us. Maybe there are a few more PALS champions who have joined. So, welcome to all of you to the very first session of this three-part industry-assisted lecture series for on systems for large language models. So now we are delighted to have such a diverse audience joining us today. This lecture has been carefully designed to go beyond the conceptual learning and help participants view generative AI and large language models from a systems perspective. And this is very critical in today's AI driven world. So today's first session focuses on PyTorch basics and the compile. This session lays the foundation upon which the upcoming session, the inference systems and distributed training will be built. One thing that I would like to emphasize is the importance of attending all the three sessions in full. There are students who attend just one or two sessions, but to get the full benefit of what is the knowledge that we are imparting, each session is interlinked. They are progressively moving from fundamentals to the advanced system level concepts. So full participation will only give you a very holistic learning on what we are trying to do in this three-part series. So we strongly encourage you to stay tuned throughout the session and actively participate in all the hands-on activities, any quiz that we are giving, and ensure that all the quiz and all the other assessment, any assignments that we are giving during the session or post the session, that is taken up very seriously. So once again, a very warm welcome to all of you, and we look forward to an insightful and a very enriching session. But before we do get into the session, I would like to reiterate on a few protocols that we will follow in all the three sessions. However, we will go over it in each and every time in each of the sessions. So if you have not already renamed your Zoom name, kindly rename your Zoom name to include your college short name. That is the only way that we will be able to identify you with your college. All of you, as you must have already figured out, will be muted all through the session. We would like to have complete auditorium type of a setup where we would like the speakers to speak and all of you to observe. But however, that doesn't mean that you will not have an opportunity to interact. So whenever there is some opportunity to interact, the speaker will, let me know. I'm going to be the moderator for the session. Along with me is Srihari. We both are going to moderate both this Zoom session and the YouTube live streaming. So whenever there is a chat box to be enabled, we will be given a hint by the speaker and we will enable the chat box, and that is one opportunity for you to interact. Otherwise, you can also post all your questions to the email ID that's flashed on your screen, askpalspmo@gmail.com. We will even post it in the chat box. Please make note of this. And if there is any questions to be asked to the speaker, please send an email to this. We are going to be moderating, looking into this email throughout the session. We will take the questions and get that answered for you. By any chance, if you have any questions and want to stop the speaker, please raise your hand. Unnecessary raise of hand is only going to create confusion. So I would request all of you who are joining not to raise your hand, but raise your hand meaningfully only when there are questions to be asked. And very important point that I would like to reiterate, we will be putting the attendance link. Make sure that you mark your attendance in the live session that you're watching. And there will also be sharing the Slido quiz link. Please ensure that you join into the Slido beforehand itself. This will be used for conducting a quiz, and we will conduct the quiz at any time during the session. Feedback link, recording, and any other presentation material will be shared post the mail. So with this, I would like to invite either Mr. Ravi Venkatraman or SKK, one of you, to please introduce the speaker, give a brief introduction on PALS, and then, hand it over to the speakers. Ravi, are you there? SKK, I think you can go ahead.
Yeah. Good afternoon, friends. I'm very happy to invite you to this industry assisted lecture from IBM, and I would like to talk about. The first lecture will be by Priyanka Naik. She is a research scientist at IBM India Research Lab and is part of the GenAI Platform team. Her prior research explored the space of cloud deployment, networking, and is currently working in the space of systems for LLMs. She has done her PhD from IIT Bombay. She is a co-author to a cloud networking book and appointed as ACM Eminent Speaker and looks forward to connecting with institutes to collaborate on tutorials and talks. And she'll be talking about PyTorch basics. Over to Priyanka Naik.
Thanks, Sujata. Thanks, Professor Ravi. Maybe I'll quickly share my screen. Right, I think my screen is visible.
I suggest that if anybody is having any queries, please put it in the chat box instead of raising your hand. Whatever genuine or however genuine it is, they are big or important because we'll be losing time otherwise. So as I please say.
Yeah, the chat box is also disabled for them, SKK, but we have given the mail ID on which they will be
Okay,
able to
right.
send the questions.
Right. Thank you.
Thank you. I can get started.
Yes, you can.
Okay. Uh, thanks to everyone for the invite to present around PyTorch and your interest in understanding the system layers of the AI world, right? So the first half of today's talk, I'll cover around how you can use PyTorch to build ML applications and what are the bottlenecks in it, which Aishwarya in the later talk will cover how they have overcome over the years, right? So I think this graph is something that all of us, or these tools are something that all of us work or use day in and day out. There's Gemini, Llama, OpenAI, right? And what are these, right? These are underliningly generative AI models, which where you give an input and you get an output back, right? And from a systems perspective, all these models run on a highly parallelized hardware, which is called as GPUs, and given by NVIDIA. These are the accelerators that are provided by NVIDIA, and there are many such accelerators available in the market today, right? And what you give as an input, right? You might have given a you wanted to search something on ChatGPT, you would have given an input, right? So what are these models handling your input as, right? So these are basically all these models that we have listed here are language models. So what do you mean by language models? It's internally just a distribution, probability distribution over words, right? So what it helps you decide is, okay, if you give a sentence that suppose Endosys or PALS is a system for is a symposium for system researchers in, and you give a dash and you don't want it to be completed, right? And your model, based on the inputs that you've given till now, interprets what should be the next word in the sentence, right? So it how does it make it understand? Because it was trained on data on, say, system conferences in India, or overall all the entire data that it gets from the internet. It has been trained over that, and it makes it understand our human language, right? So for in this example, it will say it's a system conference in India, right? So this is just an example in which the language models can be used. There are multiple ways in which the language model can be used. One, as an example I gave above, is a question and answer, where you ask, okay, who is the Prime Minister of India? It gives you answer back. Similarly, there can be a content generation as well, where you can ask, okay, create a LinkedIn post for me, or create an email for me, or help me create a base for an article that I want to enhance or write about, right? So this is kind of a content that it generates on given a topic that you provide. So similarly, another application of language models is text summarizations, right? I think most of us read lot of books, lot of papers to understand technical concepts, right? And because AI is trained to understand, or these language models are being trained to understand large amount of contents, or they understand your specific needs of a book or a paper, and because of their prior knowledge are able to understand, find the key words that are there in your paper or a book, and are able to summarize that book for you, right? That's text summarization. Then there is sentiment analysis, where you can do, okay, I gave you a WhatsApp message, or your email, and you want to understand what is the nature of which I'm actually reaching out to you. Is it a request, or it's an order, or it's something that I'm angry on you? So that kind of sentiment analysis is also what these language models support. Right, so these are just few examples of the various uses in which language models can be used to enhance your day-to-day communications or day-to-day life, right? Having said that, internally these language models need to evolve over time, right? And how do they evolve is how they are actually used, or how they are trained, right? So there are these generative AI models. We categorize them into two categories of workloads. The first is these models itself are trained on huge amount of data, which is called as the training process, right? And in the training process, it first actually collects you have these big companies which give out these models collect huge amount of data, and train your model on those data, right? This is the normal training process, which actually takes a lot of days and months if you have a huge data that the model has to learn and understand and train itself, right? But these are very large generic data sets that they get trained on. But there can be specific use cases. Say it needs to be used for a classroom project, or for a particular course in your class, or you want to work it for a suppose a industry use case. It has to be handling some bank workloads to be handled, right? And it has to understand bank related stuff, which may not be explicitly defined in the generic data set, right? In that case, you retrain the model on a smaller data set, which is very dedicated to a particular use case. That kind of process, or that workload, is called as fine tuning of that particular model. The same model trained on a huge data set is fine tuned for a particular use case that you need or your company needs, right? Once a training or a fine tuning process is in picture, you have to make sure the model is working well as you require it to be, and it is giving the correct answers, right? So in that case, there are some benchmarks available like LLM eval, which help you understand or test if the model is working fine or not. If you understand if it's not working fine, then there is a whole iterative process that you may have to give it more data set to make it more knowledgeable and handle the questions that you've used in the evaluation data set well, right? Once all this is done, it is available to us, like our end users who use the chat GPT model as well, to handle our questions or queries, right? And once how is this possible, right? You said you use chat GPT day in and day out, or Gemini models when you do a Google search, right? Underlyingly, they are hosted as a inference workload. So what I mean by inference workload or inference server is the queries that we give go to that particular model via HTTP request. These requests are directly not handled by the model, but there is an inference server that wraps your model, right? And it handles that, okay, I need not handle more than 100 requests per second on the, or give the load of 100 requests to be handled by the model, and it handles the logistics of converting your HTTP request into the actual prompt that can be given to the model, or the actual query that can be given to the model, right? And once that is done by the inference server, it is given to the inference engine, which has does its own system optimizations. That, okay, is there some similar queries coming to the model? Say we are sitting in a classroom and all of us are allowed in an exam to use chat GPT, right? In that case, you have to there would be similar kind of questions coming in from most of the students, right? So it understands that these are coming from a same family, and they can actually be batched together and given together to the model. right? All these kind of optimizations are done by an inference engine. And once it gives it the model, the response comes back, and that response goes to us or comes to us as an end user via the inferencer, right? A very famous example that's used by industries nowadays for inference engine is VLLM, which has a lot of system optimization to handle our questions or handle our queries to the model really fast with some system optimizations, right? Okay. Now we spoke about this thing. Just to summarize it in a bit more detail on what we heard till now. The first task for any model that's used nowadays is it's trained and it's fine-tuned and then it's used for inference, right? In the training process, there is a data preparation and data collection optimization step. Then it is a training space step that comes into picture. After that, it's being evolved using fine-tuning, and with that, it's evaluated, and then it's deployed on the to be used as an inference engine. Right? This is just to summarize it in a bit more detail. Right. So all these models, it's good that conceptually you have these models in and you can use this. But the question is how to use it, right? So a very famous way that industry as well uses right now is to use these models using a library called as PyTorch, which is a library over Python, right? And it's a deep learning library. So why PyTorch, right? So let's go back to some bit of history. Back in 2002, there was a need of, or there was a surge of machine learning algorithm being in place, and they required a small representation of what a human would understand, right? And a bridge between what human would understand and what a machine or a computer would understand. That's where Torch came into picture, which was a representation of your human language into something called something that can be translated into a machine language, right? Something understandable in terms of numbers or bits that can be understood by the machine language. But and that's where they proposed something called as tensors, which where the we'll come into a bit detail in some time about tensors, which were the representation of each word or each sentence that we speak could be represented into a form called as tensors. Right? And it was a very old library on Lua language. But what happened is it did not get adopted that well into the community. It was good and used by researchers and practitioners, but it was not a community-based language because it was it was very difficult to adopt to your use cases. Then Python thought, okay, we have all the NumPy and Skylab libraries already in place, which are focusing on large matrix operations or large deep learning operations. Why not we adopt what these guys wanted to do with Torch? And that's where Python and Torch came together to become PyTorch, right? And became a library over Python, right? And we spoke about, okay, it could represent it in terms of numbers and everything because they are converting it into numbers or matrices. We had to PyTorch that we have to optimize it in some way to make it faster to compile, right? And that's where this dynamic computation graph came into picture. That is, every code or every that you want to operation that you run, that is matrix multiplication or a add that you want to run on PyTorch, gets represented in a form of a graph, right? And what is a graph here? Here, suppose you want to do a into b, that is multiplication of two tensors a and b. Here, the inputs will be the tensors a and b, and there will be another output node which will be a into b, right? This is kind of a graph that internally is formed on the go, on demand by PyTorch. And similarly, if I had to finally do some operation as well up after the of the mul application, it can be represented as well. So if you wanted to do a into b plus c, this is kind of the graph that gets generated internally in PyTorch. But this is done on the go, and whenever it is just running it, it actually creates this computational graph. There is a disadvantage to it, which Aishwarya will cover in her presentation, right? now that we've heard about PyTorch, you might be wondering that we actually heard about some tools like TensorFlow, JAX, Google as well. These are some other tools that are also available in market, but PyTorch has the most established user base, and the way it is updated is and supported by the communities is well established, and it has a lot of ops supported in it. And that's the reason most of the companies are working on PyTorch instead of tools like TensorFlow that's provided by Google. Right? We spoke about Torch and tensors, right? And tensors are the basic building block of any operation that you do in deep learning when you use tools like PyTorch, right? What do you mean by a tensor? Tensors, as I said earlier, is helping you convert anything into what can be understood by your model or your machine, and that's they are represented in a form of a mathematical representation of a multi-dimensional array, right? And how do you decide what are the dimensions of the array are based on what kind of input you give, right? So if you have a one word, a word character, it can be represented as a rank zero or a dimension zero based tensor. If you give a word, it is a collection of characters, right? So it will become a rank one kind of a representation, right? A word in a sentence can be a rank one. Similarly, a rank 2 can be an example of a grayscale image. What do you mean by a grayscale image? Is the entire image can be divided into, as they call it, pixels in computer vision, and each pixel can be represented here in the graph as one unit with the dimension of how much black or white are there in that pixel, right? So that way, it is the grayscale image can have a rank of, okay, black and white, and that's why it's a two-dimensional representation or two-dimensional tensor. Now, with evaluation of more RGB kind of images that they use nowadays, there will be a three-dimensional array where each color dimension, that is red, green, and blue, will be the dimensions that you represent your each pixel in. Right? And here, suppose 256 to 53 is the dimension that it can be represented because of the three colors. Similarly, when you evolve and you want want to give a batch of images, suppose that same batch is one, whatever you had in the RGB image, that is three dimensions of 256 to 256, and the number of colors in each of the dimension. Uh, Along with that, you give a batch of RGB. So the first dimension in the shape of 4D image will be the batch size, right? So it's batch size followed by the dimensions of a particular image. Evolving it came the videos, right? So videos are actually in a way batches of images coming in, right? So here you have 64, 64, 3, the last three ones representing the dimension of a particular image. Then 16 is representing the batch size of the image, and 10 representing the total number of batches that are needed for the video, right? So in this way, a complex thing like a video can also be defined in terms of tensor. Okay, I hope things are clear till now. So we spoke about a lot of things around dimensions. This is used in terms. We took an example of image. Now to take an example of how your text that you give as inputs to your Chat GPT or any of your large language models are represented. Right. So here, suppose you gave a lot of prompts to your model. Here, say, suppose a cat climbed, the house is painted, the capital of India is, and the people of Mumbai. There are four sentences that are there in your input or a prompt. And here, the batch size of this prompt is 4 because of the 4 sentence. Right? Similarly, for each input in the batch, there'll be a sequence length connected to it. In this case, suppose my prompt was the cat climbed the wall. Here, the sequence length is 5 because I represent the sequence in terms of words. Right? So here I have 5 words. So the sequence length is 5. But bear in mind that each of these words get converted into some numbers in the a numerical format that can be represented in these dimensions that we talk about for the tensor. Right? We'll see, and this conversion is what is called as embedding. We'll see a bit details on the embedding in the next few slides. Right? Okay, before diving into embeddings and other things, we want to just get ourselves comfortable into what uh, tensors mean in PyTorch and what kind of operations are supported in PyTorch to work with the tensors. At the end, any language model you build, it's a mathematical model, right? At the end, it is internally or in the lowest level, a lot of mathematical operations that you do on these tensors, right? And what kind of ops PyTorch supports is defines how well your model can be defined in PyTorch and being trained for. Right. So some simple examples of operations that you can do on tensors on PyTorch are: suppose you want to create a two-dimensional tensor with one dimension is two of size 2 and another of size 3, and here you can do, just suppose I want tensor to be one identity metric, right? So here you can just represent torch.ones 2 comma 3, and it can be represented as here, right? It can be 2 rows and 3 columns. Similarly, you can actually create a random tensor as well, where, okay, you see, use torch.ran, which is an operation, which, and you provide the dimension 3 comma 5. So the first dimension is 3, so the number of rows are 3, and number of columns are 5, which is the second dimension. Right? So these are the basic operations that you can do to in your. So these are the basic operations that are used in the model code as well in PyTorch. Right? Before going to more complex operations that are performed on Tensor, some underlining thing or underlining concept that the way PyTorch optimizes our feel or our experience when using PyTorch, right? And underliningly, how smartly it handles, how it stores the data that we use and represent as tensors, right? So it happens that a lot of time it happens that, okay, I require the same data not to be a 3 by 5 kind of the metrics, but some say a 5 by 3 metrics, because I wanted to do a transpose and do a matrix multiplication for it. So there is a fixed type of dimension that I need, right? So internally, the data or the values in the tensor are same, but the representation is different, right? So PyTorch has very smartly separated out your physical representation, that is how what is the physical data that you want to show, as and the logical view, that is what we look or we want out for our operations, right? So the logical view in PyTorch is the tensor, which provides you the sizes of the tensor and the dimension of the tensors that we want. And internally, there is a storage class that it defines, and that stores the actual physical data or the values of the tensor. So in my case, suppose I had one 3 by 5 tensor, which actually pointed to the storage. My another transposed tensor, that is 5 by 3, would be a different tensor object, but pointing to the same storage objects, because the physical data or the numbers in that tensor, or as you call as matrix, stays the same. Just the representation changes. So the representation is stored in tensor and the data is stored in storage class. Right? This is how PyTorch stores your data. Right? So I think how you can understand that this is actually how it works or internally is. Suppose I had a matrix or a tensor of torch.1 that we used earlier. I did a dot t. This t represents I did a transpose of that same tensor, and it got into a new tensor, that is b. If I print a dot shape and a b dot shape, both the shapes will be different, because a will be, as we said, it will be 2 by 3, b will be 3 by 2. But if you want to see the physical address of the data stored here, you do a data pointer or untyped storage. It would actually give out that, okay, the address of both the tensors or the physical address of both the tensors is the same, because they are stored as same set of physical data. Right? So this becomes same unless you change the values inside that data, right? So here I had 111 111 represented as this or this for B, right? But what if I did addition of say 1, that is I did a 2 kind of representation where all the ones got increased by a value of 1, the value itself of the tensor changed. In that case, a new storage gets created for your tensor. So in this case, B gets a new storage of this tensor. And here, if you had printed b dot data pointer, it would show that it's a different storage. In the interest of time, I'm not showing it as a demo. I'll share the Google Colab code with you for this, and you can try it offline and experience this yourself. That okay, if they are just transformations and not modifying the data, the values stored are the same. But if you modify the data, the storage changes. Right? Okay. So these are just examples of how the operations can be done. That is, if you do a scalar operation, it gets applied to the entire tensor. So you can just do into two and all the things between two. And a at the rate b implies this is a metric multiplication that's represented in PyTorch. It multiplies it here, as you can see, and it represents a different dimension, a different tensor. Okay, so just to summarize, there are a lot of operations that you can do once. As the torch.one is one of the ops we saw right now. It's all collections of ones that can happen. A tensor of all values is one. Empty is a dimensioned tensor created with all the values is empty, zero, and you can put in whatever values you want. Random, as we saw, any random values can be added. And similarly, there can be operations that can be done, that is addition, multiplication, or divisions on that tensor as well. And some view operations can be done, like you want to concat the tensors, combine the tensors, transpose the tensors, unsqueeze we'll cover in the later part. And similarly, some more complex or sinusoidal kind of operations can be done as well, like cos, sine operations on these tensors are also supported by PyTorch. Right? Okay. Okay, I think another operation that we have is torch.arrange, where you say you create as you do, right? For I equal to 1 to 8, if you had a for loop, it would have run it for multiple times with each I incrementing each time. Here, the arrange tells you, okay, you can give a range for the tensor. You don't have to give it the dimension. It will be a 1D tensor that gets created with starting from 0 to the maximum value defined in the arrange, right? And this then you can modify to whatever view you want. So here I got a 1D array of 0 to 7. If I do a dot view to 2 comma 4, view is just modifying how it gets viewed for me. As we said, it will be the view changes the tensor object for you, but internal storage for the a tensor above, that is this, and this stays the same. So here I did a 2 comma 4. That means I need 2 rows and 4 columns. So it represented the data into split it into 2 rows, 0, 1, 2, 3, and 4, 5, 6, 7. Similarly, as we do a transpose internally is changing the view from 2 comma 4 to 4 comma 2. Right? So if you want to do instead of transpose, you can directly do a comma view if you know the dimensions 4 comma 2. So here it gets represented as 0, 1, 2, 3, 4, 5, 6. Right? Okay. Okay, so now we spoke about some operations. Then the question arises, are how many built-in operators provided in PyTorch? Any guesses? Okay, I think you are on mute, but I think we can discuss this later. But
No,
around,
we can, I can disable the chat box for a second. You can get responses in the chat
okay,
box.
I think I got out the output here right now. I
You
think
gave
it's
the answer?
yeah, I gave the answer. Yeah.
Not a problem.
Sorry.
Yeah.
Okay. Sure. So almost more than 2,000 PyTorch operations are possible in PyTorch, right? We just spoke some of them. There are a lot of operations that are supported, and that's why it's a well-established library. You need not worry to know and memorize all of these operations. Once, see, you want to do some transformation or some working with a tensor, you can actually go and search online on the PyTorch docs, which are very well documented, and get to learn how these operations are used for various tensors, right? These are some of the examples that I put out to you, which are the ones which are the basic operations that are used for all the operations or all the model code that we have in PyTorch. Right? So, doing a recap again, where we diverged a bit into PyTorch to understand that, okay, we build, so how do you build the basic blocks that are needed to build a model, which actually then is a mathematical series of operations that can be represented in the operations that we just saw. And it gets the data in terms of tensors, as we saw in the example above or example below, which has certain set of batch size, certain set of sequence length, each sentence having a sequence length, as we discussed above, right? So these are all kind of the basic building blocks of how the model is trained, or as well how when its model is loaded to run your queries or answer your queries, right? It is a inference server. Right. So now we are keeping talking about model, right? The base for any generative AI is the model that gets built, and we use how are these different models competing with each other is how well they are trained, or how well the computation that they have is ordered, or computation is being organized in the model. Right. So we'll now get into a deep dive to understand what these models are and what are the basics of these models that are used or built use in PyTorch or in general in any platform. This what I cover from now will be some basics on the model. This is required for your next lecture on where we'll go a bit deep into the inference side of things, where which is because very connected to how we see these models as, say, a ChatGPT application. And these concepts are needed for you for the next lecture conducted by Kavya. All right. So there are different types of LLM models as well. We saw right earlier that your LLM models can be used for various tasks. Your models can be used to encode, that is, build a representation of your features, or decode, that is, understand what you actually put in as your prompt. Right. So these are the a model can be just used in encoding whatever you got give as input. But there can be most of the models that we use right now are encoder plus decoder. That is, once it actually understands what you give as a data, but also once it understands what you give as a data, gets some analysis of that, does some analysis of the data, and gives you an output that you require. That is, it decodes whatever query you had. Suppose I had a sentence and I had the last word to be interpreted. It actually decodes and understands what should be the last word in that sentence, right? So there are a lot of examples as listed here, which are just encoder only or decoder only or a combination of both. And most of the models that we have right now is a combination of, right? And inside each of the model, there are multiple layers that are present. I won't go into the detail of it. Just remember that these each layer is a different form of mathematical operation that gets performed on the input data that is given to the model. Right? That is a basic thing that we want to learn or we need to remember. Right? But there is one specific thing that I want to go in. But before that, how will you get these models? You don't have to go ahead and build the models, right? Because these are models that require a huge set of data that needs to be trained on large set of data set and needs a lot of compute to be trained on. So you can directly use some of the models that are trained by other companies, right? So Hugging Face is a platform which actually is a hub of a lot of large language models that are trained by multiple companies, fine-tuned by multiple companies, and made available, which you can directly clone into your local machines and use it for any application. That is, you can start your own inference server with that particular model, or you can do some specific, if you have a very small specific data set that you want to, particular use case that you want to fine tune it for, you can do that as well if you have good amount of compute resources, right? And just give a stat, which almost around 2 million models are available on Hugging Face. So there would be some models that are some are around some geospatial data, some image processing based models. So these, there are multiple kind of types of models that are available, or generic question answer kind of models that are available as well. For example for it is IBM's Granite models, which are available on Hugging Face for us to be used, right? Okay. So we spoke about, okay, there are models, and the model is a collection of mathematical operations that you do on the input data, that is a tensor, right? But there is something that actually started this whole language or large language model wave. AI/ML had been there for a long time, but a large language model thing happened because of something that came in few years back around a paper which spoke about that there should be a new architecture itself, how on how these models are designed, right? And it's not the transformers that we are all aware of. It's actually called transformers, but it is a type of logic or the mathematical thing that happens in that model, which transforms how the data are viewed or understood, right? And to as we spoke about earlier, in the interest of time I'll skip it, the embedding of that model, that is converting whatever input you give as sentence to what it understands, the model understands, is a conversion that happens. And the tensor conversion, that is your data to a tensor conversion, happens using a option called as tokenizer, right? So a simplest form, if you want to use it from Hugging Face, these transformer models, you have to do a from transformers import the pipeline, and just give the name of the model that you want to run. Here, I've given a name of GPT-2. This is the Chat GPT model, right? And if you give output, if give your input, this is the input prompt that I give. This is not the UI representation, but this is a CLI kind of input that I give. The Paris is the capital of, and it should give out France, right? So that is the model. GPT model runs in the background and gets your query, and you can give it, and it gives you output. This is the simplest form of hello world in the transformer world, right? So I think how much time I have. Okay, I'll quickly go over tokenizing. As we, in simple terms, tokenizing is converting into your input into something that can be represented into input IDs or tensors, right? So the tokenizers can represent any word in form of a tensor, or it can do at a character level as well, right? So these are different forms of representation can happen. Or it can do a subword as well. If there's a cat and there's a pronoun after it, it can do separate them and split them and represent them as different tokens as well. These are just an example of different ways of representation. The most popular way of is each word is represented as a tensor, right? Okay. So we spoke about models. So model comprises of a lot of mathematical operations, and it is how well it is defined is how well it gets the inputs from, right? And it's no, as we spoke about, that it is a mathematical operation that happens. Each layer, as we saw earlier, is a different mathematical operation, and how much weightage you want to give to that particular layer is defined on how much weight is given, or a weight matrix is available in the model for each of the layer, and how heavy the weight is for that layer. It defines how much important that particular layer is to understand or to define how well the model will evolve on, right? So people who train the model come up with these weights that need to be given to this particular to each of the models, each of the different models, right? The same model with some different amount of weight might perform much better compared to some different amount of weight, right? Okay, so we kept speaking about that the whole evolution of large language models came in with the transformers, and the basic mathematical operation that made it unique is what is called as attention, right? Attention is a basic layer. Attention is a layer in the transformer representation of a model, right? And this is what the paper, the 2020 attention is all you need is a paper. If you guys have interest in reading the paper, you can actually go ahead and once read the paper as well. It's a very interesting concept that came into picture to help make more sense from the input that you give, right? So let's get an example here, right? So I had three sentences which use the word move, right? As humans, we for each of these things we have different representation. So a American shoe mole is a creature, a mole in carbon dioxide is a unit, and a biopsy of a mole is something on the skin that we want to see, right? How, as humans, we understood it that these three moles are different is because of the data that came around it to make us more understand the reference or context in which this word is being used, right? So these all these things differ based on context. So how will a machine understand that these three modes are different is how the attention mathematics will work to make it understand, and we'll understand it in a bit of a detail. I'm going into detail of the attention module itself because that's the most heavy operation that is done in the transformer architecture. And there are a lot of optimizations done to make it more lightweight and make it more understandable for the machine. And we'll go a bit detail on it in the next lecture on Thursday, right? So just quickly going over attention, each as we have spoken till now, each word gets converted into a tensor object, right? And this is called as embedding, right? Now in a vector space, if you want to do this representation, I each of these representations that we had are different values in in the tensor of they have different values as tensors that are represented. And how is that? Because each of them are associated with a different form of meaning, right? As humans, it's easy, but for a machine to understand, it says that, okay, I have something called as a mole, but it has three different representations. And you have to make sure that the model understands based on the other words in which its context has come in, that it moves to a particular representation of this word, right? So in this case, it moves towards mole. So was the American shoe mole, right? I have to make sure that this transition is identified by the model mathematically. So for that, let's get an example of a sentence like a fluffy blue creature roamed on verdant forest. And I want to make it understand that there is a blue creature in a forest. In this way, here the creature has two adjectives, that is fluffy and blue. And there is an adjective for the forest as well, that is verdant, right? And we have to make it understand that the creation has a adjective attached to it, and forest has an adjective attached to it. So here in our case, creature and forest are our focus areas for now as a simple example to understand what is attention, right? So our focus areas are on the two words, creature and forest, right? And the question I want to ask as an example is, are any adjectives in front of me? And that question I can ask for both, that is creature as well as forest. And this question that I ask is actually called as query in the attention mathematics. That is, whatever question you want to answer for a particular word or a particular embedding in your representation is called as a query, right? Similarly, a query here in this case, I have a creature which is represented as some embedding, but there will be another tensor that gets defined, which is of a smaller size, which defines that I have a query for this particular word of any adjectives in front of me, right? And I have asked question or a query. Obviously, I need an answer, and the answers are provided. Before going that, how do you define mathematically this query tensor is nothing, just a multiplication of a matrix multiplication of the embedding tensor that you define for that particular word with a weight matrix, right? So weight matrix with the embedding for that particular word gives you a smaller tensor of which is called as query for that particular word, that is Q4 or creature here, right? So this is a query that we have. Similarly, now if I, because I've asked a question, I need an answer as well. So I ask the question, I is there a adjective in front of me? Then I need an answer that, okay, I am the adjective for you, I am the adjective for you, right? So in this case, fluffy and blue should say that, okay, I am the adjective that you're looking for, right? So this answering of your query is actually represented as key uh, tensor as well, because it's all mathematics here. So here you represent in simple terms that, okay, for the embedding for a fluffy or for the embedding of uh, blue, I multiply it by something called as a new weight for the key, and in that way it represents it or gives the out answer that, okay, I am a key for the question that you asked for the particular word creature, right? So that is the key that we talk about, or the key tensor that we talk about in the attention world. Similarly, okay, you've actually thought about it as a creature, and there are two adjectives to it. You have to make sure that your answer that comes out, that, okay, is there adjective, is actually handled by the keys that you have for that particular query. So, and this is just a simple example that I gave of how I want a simple query of adjectives. And there can be multiple things that come out when the entire model or entire set of data, like a book, is given to input. There are a lot of sense or a lot of these intuitions have to be made. Right? So this is just giving you a sense that this is just a simple example to represent it. So in this case, because I want to make sense, combine the query, that the question I had, with the answer, we do a mathematical operation, which is a matrix multiplication, right? Or here, the tensor multiplication that happens. And how do we identify that this representation works only for the two adjectives that really are the keys? It's on the matrix multiplications answer. So these matrix multiplications at the end come down to a particular mathematical value, and the mathematical value which has the highest value is the answer to your query. So in this case, the K2 and K3 will have the highest values, right? So in these terms, it actually answers the queries are answered based on the keys answer the query, or in attention terms, it attends to the query, the keys attend to the query that you have asked for based on some high value, right? Similarly, okay, now we have understood that, okay, I have a key tensor, I have a query tensor for that query tensor and a key tensor. And then, okay, I have to understand, okay, for this, for my value, that is the creature, this is the representation. And that's where the value, or that for the particular tensor, you want to represent it in the same dimension as the query and the key, and that's where the values come into picture, where you answer, okay, for this particular creature, I get from various inputs that I have in the sentence, and then finally my output will be the fluffy blue creature. That is based on the creature as the input that I got into the adjectives that it had, and in this case, the value uh, in this vector dimension, or in this tensor dimension of value, the highest values will be the ones of fluffy blue. And because these are cumulatively added to form the value tensor, at the end output for that creature will not be a normal creature, it would be a blue fluffy creature, right? So that's how the final output is calculated for that uh, particular word, or this is how the machine or your model understands that this is how it should keep things or keep the creature in mind for this particular example, right? Okay, so there is something called as, okay, I don't want a lot of data to influence my output or attend to my output, right? So what is done is only the words that come in front of me in during, suppose I want to say that only words that come in front of me will make sense or give more context to my representation or my words representation. And I don't want, because in the training data, it's the full data, right? So you don't, while training, you don't want the data after coming after you to make more influence on your data. So you want to say that just don't ignore whatever comes after me, just do whatever, use data that I have comes before me. And that's where masking comes into picture, to mask your data after that comes after you, right? So in the interest of time, I think I'll conclude that there is a lot of mathematical operation that go into place just for the attention layer of a model, right? And this is computationally very expensive, because as you can see, I just gave you one word example and it got converted into a huge dimension tensor. And you can't even imagine, if you have to parse or train a book, the amount of tensors or the vectors that are represented would be really large, right? And now Aishwarya will talk about in some time that how are the ways you can understand how much heavy they are on the system with some efficient profiling. With this, I think conclude. Thank you, and hand it over to Aishwarya.
Yeah, thank you, Ms. Priyanka. So if there are any questions for the speaker, this one is we have enabled the chat box wherein you can, chat with the host or the co-host. So kindly please put your questions there, or you can also ask your questions on the email ID that we have published. Before we move on to Ms. Aishwarya, SKK, do you want to do the brief introduction for Aishwarya?
Just a second.
Yeah.
It was a very nice lecture given by Priyanka. I think next lecture is going to be by Aishwarya Chakravarti. She is a research scientist at IBM India Research Lab. She has worked in areas such as multi-cloud observability and data pre-processing, and model customization. She is working as part of GenAI Platform team. She has received her Ph.D. and MS from IIT Kharagpur. So I request the participants to make full use of their knowledge. Both the people are highly knowledgeable and with experience in the industry. I suggest that the participants should spend time in listening and in understanding, and ask your queries through email or chat box, because we have very tight time schedule. Okay, thank you. I over to Aishwarya.
Yeah, thank you so much. Thank you for the introduction. I'll just share my screen. Okay, I hope my screen is visible. I'll just do. But
Yes, it is visible.
okay, so so yeah, I'm Aishwarya, and I'll be talking more about how you can understand, like Priyanka said, right? The workloads to train or fine tune whenever you're trying to use a model or build a model, the workload is very high. It is very computationally intensive. It consumes a lot of resources, and it also is very time taking. Is a very time taking process. So first, we need to a very important aspect of this is to understand how good the performance is, or where at all, if at all there is some performance issues. First we need to understand where it is coming from, or how do we see how much resources the workload is consuming. So for that we do profiling. So profiling, PyTorch has an inbuilt tool which is known as the PyTorch profiler, and it's very simple to use. And when you run a workload, you can just specify some lines of codes in your workload, and with that PyTorch will know that okay, you want it to profile the code that you're running. So, uh, yeah. So, let us just take a simple example. So, here I've defined a model, like Priyanka was talking about the different parts of a model, right? Here, my model only consists of a linear layer. And I am passing a tensor as input to it, which is a random tensor, right? And I just want to run this model with this tensor and see where is the resource consumption, how much time each of these operations inside this model is taking. So I just need to specify these lines with profile activities profiler activity.cpu and record shapes. This is the bare minimum that we have to do. And in the end we have so what this line will basically do is it will capture a trace of the code that we are running. And if we want to visualize that code, that trace later, we have to specify prof.export chrome trace. So this is the name of the file in which you will get your trace. So this is a JSON file. Now let's see how this trace looks like. So this is a screenshot from this trace.json. So to view the trace.json, there's if you go to your Chrome browser and you do chrome.//tracing, it opens a tracing window. There, if you load your trace.json, you can see an interface like this. So in this interface, you can see there are different bars here, right? So here you must have noticed we mentioned something like with record function forward. So this means that when the code is running and PyTorch is profiling the code, this part of the code, it will annotate it as forward. So in the profile trace.json, you can see that this is the forward function that it is tracing. The length of the bar denotes how much duration it is on for. And then inside forward, you can see linear. So linear is our module which we defined. And inside linear, we have ADMM. So this add mm is basically addition followed by multiplication. So this is a kernel. Now, we ran in this code, this whole workload runs on the CPU itself. So we can see this entire workload which runs on CPU. And if we click any of these bars, for example, I have clicked this 8 and resolve conjunction bar. Here we can see that it displays many information such as the category, that it's a CPU operation. Then what is the start time of the operation, what is the duration, and the different inputs that goes into the operation, the strides, the dimensions that Priyanka had spoken about earlier. So in addition to the time, the latency that it takes to run a particular model, it also shows the memory, how much memory is consumed to run this model. So in the same code, if I just add this line, profile memory is equal to true, PyTorch will know that we also require it to profile the memory for that particular operations. Now, just one thing to note here is all of this profiling memory with or without, these had different types of overloads on your overheads on your workload. So it might take a little bit more time to run this code with profile memory is equal to true. And here, if I showed you a way to see your trace, now this is one more way in which you can print the output of whatever profiling information is captured in the form of a table in the console. So here, if you specify profile key averages table, and you can specify any sort by metric here. I have taken CPU memory usage because I want to see the memory, and then I can specify some number of rows limit. So this is that kind of table that you can see in your output console. So there you will, for these are the different ops which are running. So you can see linear, and then linear will have add followed by matrix multiplication, then transpose, then strided, lot of expand, all of these, right? So for each of these operations, you can see how much CPU it took, how much CPU as the fraction of CPU which is available, how much CPU as a fraction of how much CPU the whole workload consumed, and the total time duration for each of these operations. And in addition, you can also see the memory because we sorted by memory. So it shows the maximum, the op consuming the maximum memory at the top. So total, you can see the forward block that we had written is consuming 200 bytes. So in this way, these are the informations that memory profiling gives us. And in addition, you also get the number of times a particular op is called. This was a workload on us on the CPU. Now, what if we want to run something on a GPU, an NVIDIA GPU because it's the most popular one, right? So here, to run this, there'll be some changes to the workload code as well as the profiler code. So the workload code, we have to now specify that the model has to be on the device CUDA 0, that is our GPU. Similarly, we also have to move our tensor, which is the input tensor, to the CUDA 0 device. And then when we are specifying the profiling part, we have to specify profile activity.cuda to tell the PyTorch profiler that you also need to profile whatever is happening on CUDA in addition to what is happening on the CPU. So, and a similar way you export that trace. So I just urge you guys to try this out. When you'll get the PPT, you can maybe try out this code on your own and see what is the difference in the trace JSON output that I showed you earlier, and what you're getting after running a workload on the GPU and tracing it. So I have a pre-prepared profile for which I generated by running the GPT-2 model, just for your information, and maybe you might find it interesting. So I'll just show you that quickly. So here I have preloaded it. So this is the Chrome tracing tab which I've opened, and I have loaded the trace.json. Sorry. Okay, I have loaded the trace.json beforehand. Here you can see, if you look at the module, it is called GPT-2 model. So which says that we are in fact looking at the trace of the GPT-2 model. And here, if we keep going deeper into the different blocks which are present, we can see there's a GELU activation, there's a convolution, then there are some transformer blocks also, there's a 8 and dropout. So you can see different ops which are there. And if you click on any of these ops, for example, I click on 8 and dropout, I can see the 8 and dropout name of the op, the category, the duration, time, input dimensions, etc., etc. And in addition, like I said, we had run this GPT-2 model on CUDA, on the GPU. So we also, in addition to CPU, we also have a GPU part. In the GPU part, we can see, um, just a second. Yeah, if we look into this thing, we can see that the different kernels which are running on the GPU. For example, this is the attention kernel. So I think Priyanka spoke about the attention mechanism in detail. So this attention mechanism is implemented in for the GPU. This is a Cutlass library which is used to implement this for the CUDA GPU. And here you can see there are different very granular information which you can get. If you know a little bit about CUDA, you might understand it talks about how many SMs, the blocks per SM, swaps, etc., etc. So this is how this is the level of information that PyTorch compile gives us. PyTorch profiler gives us. And yeah, I urge you to go ahead, check it out yourself, and maybe you'll find out some more information. So now the next step after the basic, I think the reason to know the performance is also to understand if the performance is not good, then we are able to find out where the performance is not good. And then after that, we want to improve the performance as well. And to improve the performance automatically, PyTorch also provides a tool which was introduced in PyTorch 2.0. This tool is called the PyTorch compile. So a bit brief background, right? So Priyanka talked about the dynamic graph computation graph generation in the beginning when she started talking about PyTorch. So basically, just a recap, that thing, right? How PyTorch works is, when you run a module in PyTorch, it will go line by line and execute your model line by line. And as it goes from one op to the next, it will add the new op to the computation graph that is generating. So the computation graph is generated dynamically as the execution proceeds. In the end, we do get a graph, but that is after we have fully run the code, right? So this mode of execution is known as the eager mode. And it's very easy to use. So in the sense that when you're running a code and you encounter a place where there is an error, you just stop there, and you know this is the portion which is causing the error, and you go ahead and fix it, right? So it's very easy to debug. And this made PyTorch, because PyTorch was by default has the by default the eager mode of execution. So people found it very easy to accept, to adopt for their for doing deep learning. So if around the time 2018, when all of this was new, if we look, so this graph basically tells us how many repositories were there which used certain DL frameworks. And this is for TensorFlow, this is for PyTorch, and this is for the remaining, right? And you can see PyTorch has a very little share at this point of time. TensorFlow was primarily used, but TensorFlow, like Priyanka also mentioned, it does not by default work in eager mode. It works in a different mode, which is the graph compilation mode, and which is a bit more difficult to it's a little less flexible compared to PyTorch eager, right? So because of the ease of use of PyTorch, the adoption of PyTorch increased like anything, and right now at this point PyTorch has a huge share of repositories in the in GitHub which use PyTorch. It's primarily PyTorch heavy. The entire ecosystem around DL workloads is dependent on PyTorch. But although the eager mode is very useful, it's easy to debug, it's flexible, there's a problem. The problem is, because our deep learning workloads are typically very heavy, you want to optimize its performance, you want to optimize the resources it can use. But the mode of the dynamic execution mode or the eager execution mode presents very few opportunities in which you can perform optimizations beforehand, because your dynamic the computation graph is being generated dynamically. So at any point PyTorch only has visibility of one operator that it has encountered. It does not know what else is there in the rest of the graph. So if it can perform any optimization, it will be very local to that particular operator. It won't be able to perform any global scale optimizations. And global scale optimizations is there are a huge scope of global scale optimizations in these kind of DL workloads, and it's very important to find and take up those opportunities, right? Use those opportunities to save resources. So that's where the graph mode of execution again made an entrance. So TensorFlow was graph, by default graph had the graph mode of execution, but then PyTorch brought eager mode, and eager mode gained a lot of attention from everybody, lot of adoption. But now people are realizing that graph, although eager mode helps us build models quickly, it's also not the most optimal way we would want to go about these kind of workloads. And hence PyTorch decided to implement this graph mode of execution using torch.compile. So basically torch.compile gives us the graph mode of execution, which means that before the entire code is run, the whole graph for the whole computation graph for the whole workload is generated. And after that, there are optimizations which are performed, and then only it is run on the hardware. So this torch.compile is nothing but a just-in-time compiler for PyTorch. What it does is it generates the forward and backward graphs for a given workload. Then it converts those. There are different. So in those graphs, there will be different operations which we defined in the form of PyTorch operations, like Priyanka mentioned. So there can be linear, there can be convolutions, there can be softmax, etc., etc. Like the 2000 different operations are there. So those will be converted to a limited set of operations, which are very simple operations like matmul and add. And then after that, the entire graph will be compiled and optimizations will be applied to it, which will then be run which will then be used to run on the hardware. So it's very easy to use torch compile. So when you define a particular function or a module, you just annotate it as with @torch.compile on top of it. So this is a function I have defined. It takes in two tensors, performs a multiplication, then an addition, and just specifying torch.compile would make PyTorch aware that this needs to be compiled before it is run. So for the first time, when you're calling foo with two tensors in tensor inputs, it will first compile the whole thing, and then it will create a compiled artifact, and then this compiled artifact will be run. If you change nothing and run it again, it will use this compiled artifact. It will not do a second compilation unless nothing changes. So just to demonstrate, quickly demonstrate a speed up. I don't have the workloads right now, but I ran these experiments separately. So I ran a MobileNet V2 model with a dataset ImageNet, and it had 1,000 sample images. And we took a batch size of 32. I think all of these words make a little more sense to you now that Priyanka has given a very good introduction to all of these concepts. And we run this workload, and what we get using torch profiler is we see that without compile, the average latency is around 26.55 milliseconds, and the throughput is around 1200 samples per second. But when we use compile from the second run onwards, the average latency goes down to 17, which is a 32% decrease, and the throughput goes up to 1791, which is almost a 48% increase. So which is, this is just for a very small workload. The kind of workloads that we have these days with the LLMs and the different kind of image generators and training of those models, it's huge. And this kind of uh, impact, this even the small impact can translate to a huge resource saving and huge improvement in performance. So now let's just try to understand what happens under the hood when we run torch compile. So like we mentioned, right, there are three steps. First, there's a graph acquisition or capture step, which in which the graph, when in which a given function, so here we have a foo function which has a convolution, a batch norm, and a ReLU. This is converted into an fx graph. So this graph is known as an fx graph. This is a term that is used. And to aid this transformation, this graph capturing, there are two tools which work under the hood. First one is Torch Dynamo, second one is AOT Autograd. We will go deeper into all of this just after this. So the next step is graph lowering, where uh, each of these operations, these complex operations like convolution, 2D, batch norm, these are broken down into smaller operations. So conv 2D is broken down into convolution and bias. Then batch norm is broken down into subtraction of mean and divided by standard deviation. ReLU is broken down into max. So that the number of operations, the set of operations that is used here, that is a limited set. And then after we get the graph with very simple operations, this is now sent to the compilation step, where a backend compiler will compile it to hardware specific code depending on where we are running the hardware. So by default, there's a backend compiler which is provided by PyTorch, which is called the Torch Inductor. There can be many different types of backends. For example, TVM, XLA, these are known DL compilers. And so Torch compiler also support these backends. And you can also create your own backend. So we'll get to know a little bit more about all of that as these towards the end of these slides. So once you have you have the model script, you annotate with torch compile, and you run it. It goes to torch dynamo. Torch dynamo will convert it to an fx graph, and which will have the different torch operations, and this representation is called the torch ir, or intermediate representation. Then this goes into autograd, aot autograd, which converts it into fx graph, but converts all these ops to ATEN or prims ops. So ATEN or prims are a different category of ops, which are the lower level ops. Just these are how they are named. And the IR that is generated is called ATEN or prims IR. And finally, this goes into inductor. There are several alternatives to inductor, but we'll talk in details about inductor only in this presentation. So then inductor will then generate different backend specific codes. So if you want to run your workload on, say, GPUs, it will generate Triton code. If you want to run it on CPU, it will generate C++ or OpenMP code, and so on. So let's talk a little bit about the different tools. So first is Torch Dynamo. Now Torch Dynamo is the main just-in-time compiler, and it helps us to basically it is designed to allow this graph mode of compilation. And by now we know it emits something called fx graph. Now what are fx graphs? These are computation graphs which contain different PyTorch operations. Now, how is this enabled by Torch Dynamo? The working of Torch Dynamo is a little bit complicated. But it's very fascinating. If you want to dig deeper, I have shared some sources, you can go through them. I'll just give a brief about how it works. So when you have a Python code which has some PyTorch operations and you want to execute that code, as you start to run that code, it will start executing each of the lines, right? Now, the way Python code execution works is it converts your code into different frames. Like each function is a frame, and each function calls, if it calls a sub function, that becomes another frame. So there are different frames, and these frames are evaluated one by one, and to finally get the output of the entire code. Now, what Torch Dynamo does is, when this frames are executed, so when each of these frames will they contain the Python bytecode. This Python bytecode is then executed by C Python interpreter typically. Now, what Torch Dynamo does is it will take this Python bytecode from the frame and it will convert it into an FX graph. This FX graph will have PyTorch operations. So it will perform bytecode analysis at this point and get the graph. And after this graph is, it obtains this graph, all the steps that we talked about earlier, like lowering, compilation, all of that will happen, and it will get a compiled FX graph. Now, this compiled FX graph will have modified bytecode. This will be converted into a modified form of the bytecode that it had taken. And this modified bytecode will then be written back into the frame, and then that frame will be executed. So it basically hooks into this process of frame evaluation process of Python and makes changes there itself. So it's a very fascinating and complicated concept, but yeah, it's very if you would like to know, you can go ahead and read it. It does exactly what uh, is required for torch compile. Although, to support this whole thing and to make sure nothing it does not fail or break somewhere, there are a few features that Torch Dynamo had there are few features which have been built into Torch Dynamo. First one is graph breaks. So you saw that there's an FX graph which is generated and it only has PyTorch operations. Now, what if when we are converting the bytecode to this FX graph, Dynamo encounters some code which is not PyTorch code? Typically, in case of other tracers, what happens is it will break at that point and the code will exit with error. But Dynamo has to support this because there are a lot of other ops. So in a deep learning workload, apart from PyTorch, there are different other libraries also which are used, which may not be known to PyTorch. There are many user-defined functions as well, so which may not be known to PyTorch. So to handle those, there's this concept of graph breaks. So what PyTorch Dynamo does is, as it is going through your bytecode and trying to build the computation graph, if it encounters any piece of code which it does not know, which is not PyTorch, which is something completely new to it, it will stop the graph capture mechanism and it will fall back to the C Python interpreter. So it will say that this is a code I don't know. So so it will send it back to this execution and say that you execute it because I don't know this code. And then when again there will be PyTorch ops, again it will encounter new PyTorch ops in that flow, it will again start tracing that and generating the FX graph. So what we have is it was a graph, it was generating a graph, then there's a break, which is the graph break, and then again it resumes graph construction, which is a new graph. So this graph breaks, although it impacts performance, it does help prevent the code from exiting. So I'll just give you an example. So for example, if you look at this code, here we have a function which has a cos operation and a sine operation. And we just return the sum of those, and we specify a torch compile on this, right? So if we just, without any changes, if we see what is the FX graph that is generated, it will look something like this. It will have the different inputs x and y. It will have the a and b variables which are generated, and which has the sine operation and cos operation, and it'll have add is another operation which is being performed here, and finally the output. But now I introduce a line which is printf, which says print hello. So print is basically a built-in Python function, not PyTorch. It is not PyTorch native. So now if I generate the fx graph, what will happen is you will see there are two graphs which are generated. First has x, y, a, b like before, but it does not have add because now it has hello. So whenever when the execution was taking place and the fx graph was being generated, Dynamo generated a graph up to here, and then the graph generation stopped, and then it fell back to C Python interpreter where this hello got printed. So you have a print for hello here, and then again a new graph got generated for this part, which is represented here. So you have a and b, which are the variables here, and then you have the add operation, which is here, and then you have the output. So now you have two fx graphs, and here if you do dynamo explain, you can see that the graph break count is 1, the graph count is 2 because there are two graphs, and you can also see the break reason for the graph break, which is the built-in print. So the print basically caused this graph break. Next feature that Dynamo has is guards. So now so one major benefit of pre-compilation comes from the fact that when you have a deep learning workload, you are compiling it and you're generating a compiled artifact which is being run on a hardware. Now the next time you run it without changing anything, it should not need to compile it again, right? So this is one feature which is enabled in Torch compile with the help of guards. So what it does is it it basically specifies certain conditions under which portions of some of the compiled artifacts which have been generated previously can be reused if those guard conditions are met. Now, if there is, so for example, if you say that if you have a code and you say you generate and you run it on GPU and under this compile mode, so some compiled artifacts are generated. So in that case, you can say that if I run this piece of code again on GPU without any other change, you should directly take the artifact which was compiled previously. You should not do a recompile again. You don't need to do a recompile, right? So that's how you specify that's what you need the guards for. So these specify different conditions, and these conditions, like I said, could be devices, could be data types, shapes, values, etc. If these guard conditions are satisfied, then Dynamo will take whatever compiled artifacts it has from before and reuse it. But if any of these guard fails, for example, earlier I had run it on GPU, now I am running it on CPU, so it will know that, okay, this guard condition was there, which said only use it when the device is GPU, but now it is being run on CPU. So we cannot use it. So that guard failed, and so I have to do a recompilation. So I'll just give an example of guards as well. So here's this small program which calculates the square of x. Then it also takes an n as input. And this n, if it is greater than greater than 0 or positive, then it will return some value. If it is not, then it will return something else, right? Now we generate a random tensor x, and then we run this function several times with different values of n. So first we run it with n is equal to 2. Now here some guards are generated in this case. Here the guards which are generated, if you look closely, you can see that L of n is equal to 0. That is the value of n is equal to 2. So because n was specified as 2, it knows that if I give n is equal to 2 again, then it should, this is a this is a guard here. So I can reuse it. Similarly, now next time when I run it with n is equal to 3, this guard will fail. And because now n is not equal to 2, n is equal to 3. So it will know. So here you can see this recompiling function triggered by the following guard failure, n is equal to 2. Because now n is equal to 3, so this graph failed. So there is a recompile which is triggered. And now the new uh, guard is generated, which is L of n is greater than equal to 0. So it is saying that, okay, if it's positive, then I will use the compiled artifact because both 2 and 3 were positive. So it generalizes it to n being positive. Now I run it with n is equal to minus 2. Now the previously generated, both of the previously generated guards, that is n is equal to 2 and n greater than 0, both of those fail and another recompile is triggered. So if you look here you can see that because of both the failure of both of these guards, a recompilation has been triggered. So these are some of the features. There's another important feature called dynamic shapes in Torch Dynamo. You can also take a look at that. For the interest of time, I will not go deep into that. Next component is AOT Autograd. Now you have the inference workload where you are doing a forward pass on your model. That is, you are going from the beginning to the end of the model, performing all the operations. But what if you want to do training? You have to, in that case, you have to go from the start to the end, and then you have to propagate the error back from the end to the start. That is the back propagation. You have to do the backward pass as well. So AOT Autograd is the component which comes into play when you also have a backward pass. So here AOT Autograd helps to capture both, after the FX graph of the forward pass is generated, AOT Autograd helps us to capture the backward pass as well. And in this case, it will generate this backward FX graph ahead of time. So it is called a AOT, or ahead of time autograd. So here, if you see, when this when the AOT autograd turns on, it will generate the backward FX graph. So it'll give as output. In the end of this step, we will have the forward FX graph and the backward FX graph. And then after that, it will decompose it into the lower level operations, which we had mentioned earlier. That is the graph lowering step, and it will perform a min cut. So here the main objective is to reduce the memory lookups or the memory accesses. So if it will take decisions such as whether we want to recompute certain values, or whether we want to store certain values, because at this age, some of the values which are computed in the forward pass will also be used in the backward pass. So it takes this decision of what to do, whether to compute or store, and thereby perform some sort of optimization. And finally, at the end of this step, we have the FX graph with in the lower level IR. And next is the torch inductor. So torch inductor is, after the FX graph is generated, it is passed on to the inductor. And inductor is the default compiler backend which is provided by torch.compile. So if you do not specify any backend, it will fall back to torch inductor, and it will detect on which your workload is running, on which hardware your workload is running. It will output Triton code for GPU, and for OpenMP and C++ code for CPU. At this stage, there are certain optimizations in the torch inductor. There are certain optimizations which are performed. So some very simple optimizations are operator fusion, where so here you can see there's a multiplication followed by an addition. So here, mm, the Z variable is created and then it is accessed again. Now there's this operator fusion optimization, which can be uh, to compute this multiplication and add b to it at the same in the same op, so that this memory access of accessing Z, storing into Z and retrieving from Z can be removed. So this is one optimization which is done. Then there's a dead code removal. So if you are running the code multiple times and there's a certain portion of code which is not being used at all. For example, here the y is equal to sin x, the calculation of this makes no sense. There's no point of calculating this to get the output. So here you can remove these kind of lines which are dead code. So you can just remove that and reduce some computations. So these are some very simple optimizations which are done. So I'll just give a brief example to go back to where we started from the profiling aspect and how these all comes together. So there's this operator fusion which we talked about. Now when we have not specified any torch compile here, and we just run it in eager mode, if we generate and see its profile, we will see that this is what we get. This is the profile of that, where we can see there's a block called foo. And if we enlarge this block, we can see there are two CUDA launches which are happening. So that means there are two CUDA kernels or two GPU operations which are being started. And if we look deeper in if we look into the GPU profile, we can see there are these four operations which are performed. So there's this rand, which is the rand creation of one tensor, then there's the another rand creation of another tensor, then there's this multiplication of first multiplication, and then there's this addition. So there are four operations which are performed. Now what we do is, in this code we add torch compile. So now we want to see how the profile changes. In this case, if we run torch profile, we will see that here is we get something similar. Here we have the foo, but we also have something new which is called the torch compiled region. So anything which is compiled will come under this torch compiled region. And then we have foo, and under the foo we will have several other things. For example, we have dynamo, there autograd, all of this will come because now we are doing torch compile, right? And then if we look at the kernels which are running on GPU, we can see there's one rand, there's another rand, so no change to this. But now there's only one kernel, which is the fused kernel. And this we can also view this when the output Triton code which is generated, in that also we can see. So we will have something like this. There'll be a fused kernel. So out Triton POI fused add and mul. So this kernel is a fused kernel of add mul, and it has both multiplication and addition inside. So yeah, this is how fusion looks like if you profile it, and you can see, you can do these experiments yourself. And apart from Inductor, there are other backends also which are possible. So like I mentioned earlier, there are TVM backends, XLA backends, Onyx backends, all of those which are supported out of the box by PyTorch. And there are other uh, accelerator specific like IPEX and OpenVino, which are specific to certain accelerators which are built by, say for example, IPEX is built by Intel themselves, right? Something like that. So in the similar way, IBM also has its own accelerator, and we sort of have our own backend to run compile code for that particular uh, uh, accelerator. And similarly, you can also define your custom backend. So if you have a different accelerator hardware, you can define custom backend. You just need to define backends for both Dynamo and Autograd, and you need to specify, you need to write the function in such a way that it will take the fx graph as input and return the forward function of the compile graph as output. And some more utilities which are provided by Torch Compile. So we have three different modes. So any user can use these modes. If you specify default, by default, it will do an efficient compilation and it will take no extra memory, and the compilation time will be low. But if you do something like max auto tune, it will give you the fastest possible code, but it will take a long time to do the compilation. Now, if you do full graph is equal to 2, it will run only when you do not have anything which is causing a graph break, and it will make sure you do not have any graph breaks in your compiled artifact. And finally, you also have some utilities where you can see the compile time. So the time to compile in each of the passes, how much time it took to compile the code. If you want, you can specify how you can limit the number of times a particular function is recompiled by setting the recompile limit. You can do torch dynamo explain, and you can display the graph breaks and their causes like we showed one output. You can, and if you want to do a fresh compilation from before, you can just do reset, then it will delete all the compile artifacts it has previously generated and stored. Finally, the something that came in very handy for me was doing the torch logs. So if you specify torch logs as all of this or some of this or subset of this can help you get a sense of what are the graph breaks, what is the output code which is generated. You can see the guards, you can see what are the graphs and sizes of the graphs, the fx graph, the core, the one with the torch IR, the one with the Aten IR, everything, right? So all of these are very helpful if you're trying to learn this. I have shared some of the material that I had used, so please check these out if you're interested. Yeah, that's all from my side. Thanks.
Thank you. Thank you, Aishwarya. So if there are any questions, this is a time for us to ask questions. There were two questions, but very generic ones. One of the first question that came was difference between LLM and generative AI. If you can briefly mention on that?
Yeah, I think generative AI is a term for used for these large language models. They are used interchangeably. And because they are used to generate the text, that's why they are called generative AI. But most of the language models that are used to use that generating that text is are called as large language models or LLMs. Yes.
Okay, so if there is any follow-on question on that, whoever asked this question, please let us know. Then there was a second generic question which said, I'm interested in learning in deep learning and I'm planning to hop into NLP. Can you please suggest me a method to learn these? And
Okay, I think we are system experts, but in case you are interested in learning NLP, there are some courses from professors in Stanford uh, and likes like that, which we use ourselves to just get into this phase. So they can be an initial thing that teach you the basic building blocks on getting started in this space.
okay, thank you. Let me check. And there's one question from Abhishek Naik. He's asking about agentic AI. What is the
Okay.
question? I mean, there's just put a question mark saying about agentic AI question mark. Abhishek, if you're there, you can raise your hand and I can unmute you and you can ask your question. People who are raising their hands, I hope you have a question. I'm going to ask you to unmute. Kotresh, you want to ask a question? Akhilan, you want to ask a question? No, I think they're just randomly raising their hands. Are there any questions for the speakers? We'll wait for a few more minutes. See, you can't raise your hand because I'm unable to find out whether you're raising hand for asking questions. You can please put your questions on the chat box. And also use the email ID that we have provided. Either of that will work. Okay, there is a question from Hussein. He says, what is the buzz about the TPU and difference between GPU and TPU?
I think that's a very relevant question for us as well. So, this is the difference between TPU and GPUs is the underlying architecture that they have, right? So, GPUs are general processing unit which use the similar architecture of control flow that our typical CPU cores as well use, where for each instruction that you want to run, you fetch the data, right? This is good for general computations that we've been using for long periods now, but they are not optimized for kind of computations or instructions or the ops that are used in the data learning or machine learning models, and they are actually more data heavy, right? Whatever operations that we do, as I gave an example of tensors, whatever operations that are done are on these huge tensors, right? So these are data heavy operations. So instead of doing it more instruction heavy or more control flow dependent, what done is like architectures like TPU or tensor processing units, they follow a data flow kind of architecture where the data is first fed into your system or your chip, and based on the data that's there in your chip, the corresponding instructions required to operate on them are actually fetched, right? So that the architectural differences, GPU is a general purpose control flow architecture, TPU is a data flow based architecture. In fact, IBM also has its own Spire accelerators used for AI applications and running inference workloads that also follows the same data flow architecture, right?
Hussein, if it answered your question, do let us know. Or if there is any follow-on question, we can definitely take it up. There's one more question on the chat box. I would not know how to spell this, but I'm reading it out. Excuse me if I spell it wrong. So it says, I'm interested in learning GPU like it says CUDA. How do you spell that? along with the AI data science, is there any suggestions to learn?
Yeah, I think
CUDA.
he
CUDA, is it? I don't know.
yeah,
CUDA.
yeah, it's CUDA. It's the
Uh,
GPU's programming language. It's a good area to learn and pick up skills on because it's a niche skill not everyone has control on. So, one thing I'll tell you, I think you need a good base of understanding C++ because that's a similar programming flow that CUDA also follows. So, once you have some hold or command over C++, you can go on any online tutorials to learn CUDA. Right? I
Yeah,
think
I
Ashwin can add as well. Yes.
Yeah, so just wanted to add that even NVIDIA website itself, there are some learning resources, and those are pretty comprehensive. So if you want to learn about GPU, I would suggest start with the basics of the architecture of GPU. That would help you understand if you're writing a code, why you're writing it in a certain way, and then you can take basic CUDA lessons. And yeah, I think that should be good to start with.
Any other questions? There's one question. I mean, again, very generic in nature. It says, I am someone who's interested in AML, confused on the roadmaps. For that, I see it on the internet. Can you give a little insight or the correct path for learning AI/ML?
I think, as said for another query as well, learn your basic concepts well around what are the architectures being used for these models. Uh, and if you're interested in the system side of things, understand things that we discussed right now on how the underlying resources like the GPUs or the memory for the GPU are used. If you're more on the application side of things, understand how these inference engines work and as someone pointed out, what do you mean by agentic AIs? What different agents would run on, and how will they communicate? All that thing is, I think, very hot right now, and people are moving into this space. So that can be a good futuristic goal for you to learn and understand. But I think basic understanding of the model architecture and ML algorithms is important. I think
Mohammed, I hope that answers your questions. If there is anything to ask further, please let us know. The next question says, suggest me some strategies to deploy PyTorch models in production environment.
Yeah, I think they work as is. I mean, if you want to deploy, you can run these PyTorch code as a code actually as your you can deploy it like build an image out of your PyTorch code and build it on any cloud environment because at the end it's an application that gets built and it can run on any accelerator like GPU. So if your pod has GPU enabled, then or your cluster has GPU enabled, and you can create a pod that on your cloud environment, which is GPU enabled or in any accelerator enabled, and your PyTorch code can directly be running on the GPU once you specify the device to be used as GPU in PyTorch. Right? Similarly, there for other accelerators, you can define PyTorch.device or torch.device in your PyTorch code, and it can run on the any accelerator. And most of the cloud environments nowadays support GPU acceleration. Yeah. Thank you.
Okay. Akilan, I hope that answered. Akash, I have unmuted you. You want to ask a question? Akash? Pallavi, do you want to ask a question? Okay, I'm not sure. Now, there is one more question from Shweta of Presidency University. And her question is, what are the open research challenges in LLMs, which is open for research? I don't know. That was clear?
Yeah.
Yeah, Ashwini, I want to take it up.
Yeah, I think I can start, but so it's as per what I would say is it's a huge domain. It's something that there can be different uh, areas where you can do research on. If you want to work with LLMs, like Priyanka also mentioned, right? If you want to do some research on the application side of things, then there are okay, first thing I think would be on the application side of things, it would be what are the different innovative ways you can use LLMs. There are already many new different products and services which are coming up which use LLMs. So maybe you can think of something like that, and you can find out a niche area which requires which has some problems, and LLMs can help you solve those. Then there, from the model standpoint, there are always search for better models, so which have a better performance. There are certain cases you can look up the different say performance of look up read up about the performance of different models, where they are failing. If certain even chat gpt does not work always, there are problems like hallucinations, and then there are problems like when there's a long context and um, ChatGPT forgets what you said earlier, right, and gives a very generic answer. So there are different problems like that which people are trying to address. I think that's something also which you can uh, look into, try to come up with, change the model architecture or come up with novel model architectures. And then on the system side of things where we work, I think there are the major issue is this GPU resources are very scarce. So we are trying to optimize the use of the resources, be it compute, be it memory, be it the communication overheads when there are multiple GPUs which are working, which you are using to run a particular application. So coming up with different algorithms to fix the issues which are creeping up, and find out new areas where there are bottlenecks, and you can address those with some optimizations. I think all of these are there. But what I would suggest start getting started with is finding out that area which interests you, and then it will probably help you to dig deeper and read some papers in those areas if you're interested in research. Yeah, I think that's all, Priyanka, if you want to add something.
Yeah, I think that covered the breadth of areas of
Yeah.
your work on. Yeah, thanks.
Okay, just quickly, last two questions. You can see how fast you can answer. We just need to run the quiz also. How to efficiently debug vanishing gradients in PyTorch models?
Uh, I think I'm not an expert in this space. We are from the systems background. I think this is a question. Maybe in future, if you have some MLAI expert joining you, I think they can be able to handle that question. Yeah.
Okay, so Pandi, you may have to look out for an answer, or we'll try and see if we can, get this answered through some other expert. So what we'll do now is, we have shared that quiz link earlier. I hope all of you have joined the quiz link. I'm going to share it again. Hari, please share it in the, our YouTube streaming also. If you have not joined, please join. I'm going to, lack of time, I'm just going to quickly share the screen. 1 second. Already we have 910 people there. So, okay, I hope my screen is seen.
Yes, it is. It's
Thank you.
just loading up. Yeah, it is visible.
Okay. So, you all please stay on to your browser wherever you have logged in. Do not operate on the Zoom screen. The Zoom screen is not an interactive one. So, you will have to click on the link that I have given, and it will ask you to register with your name. Already many of you have done it, and you need to be ready. I have not started the quiz yet. Priyanka and Aishwarya were kind enough to give us 15 questions. I've just picked up 5 questions from that, and we are sharing it today here. This is just to quickly test your knowledge. Rest of the question we will relay it as a final quiz at the end of the series. All the 3 sessions are over. We will do that. So without any delay, I'm just going to get the session quick quiz started. You'll see a question with the 3 or 4 options. It's a multiple choice questions. You'll have to click on be on your browser, give your answers on the browser only, not on the Zoom screen. I hope the instructions are clear. And also it is a timed quiz. So there is a time limit for it, 20 seconds. So I'm starting with the first quiz now. I hope all of you are able to see on your browser. The first question is there. There are 4 options and one of them is the right option. So you'll have to click on the right option. Okay, all of you have said option B as at least 50% of you have said option B. Let us see. And option B is the right answer. Moving on. See, we see that out of 1,000 people who have registered, only 300 have taken the quiz. I hope all of you are, quick enough to take the next question. The next question is there. Please be quick enough to do that. Okay. And again, here option B is the right answer. 60% of you have got it right. Moving on to the third question. Okay. It is option B, which is fine tuning. Most of the time we do all of the above as the right answer, but that is not the right answer all the time. Going to the question 4.
I think, Sujata, for the previous one, A was also a right option. So I think for the A option, if someone has opted for it, should also get a grade. I think both the options, I did not realize it only should be one answer. So I gave both the options. So I think
Oh, okay.
question, LLM workload training is also LLM workload.
Okay. Now I don't think I can change the configuration, but anyway, we'll make note of it for the final quiz.
Sure. Thanks. Thanks a lot.
So here A is the right answer, Priyanka.
Yes.
Okay, so let's see, 44 percentage of you have got it right. That is the fourth question. And we are moving on to the fifth. Maybe we overlooked it when we configured, so we'll have to be careful. Hari, the next time we have a multiple answer, we'll have to be careful about it. And is this the right answer?
Yes, it is.
Okay, 62% have got it right. So, and I see that 857 have participated in this quiz. So that's all we had. It was just a fun interaction that we wanted to see how much you have learned from the session. We'll quickly see the leaderboard. If you can return back to your Zoom screen. We don't know which college you're all from. Only I can identify Deep Sham from MEPCO Schlenk. Congratulations. Jerry, Suresh, Inzira, and Pandi. Pandi, I remember you asked a question as well. So maybe some of you had said the option A as well, and maybe you have a 5 on 5. But Jerry is at the top with 1 minute and 30 seconds. That's the fastest finger. So that's all we had for the quiz. SKK, you want to conclude and give a thank you
Yeah.
note? Yeah.
Friends, actually, I was listening and I was going through all the presentations by with Priyanka and Aishwarya. Quite an interest, sorry, quite an interesting subject that we had for the last 2 hours. And I would like to thank both Priyanka and Aishwarya for the kind of preparation and coming over here and making a presentation and listening to the questions, few questions that came up and answering all the questions because they are experts, I could make out. And I would like to thank PMO for the kind of organization and Mr. Ravi, my co-champion, for joining us. Even though he was not able to speak, there was some problem on the microphone. And also the participants who have come in large numbers to attend this program, I would like to thank profusely. Thank you very much.
Thank you, SKK. So, to all the participants, the next session is on Thursday. We are going to be learning about inference system from Ms. Kavya Govindarajan. She's again a research engineer from IBM Research Labs. So, a couple of points that I would like to mention here. If those of you who have not been able to share the attendance in the earlier given attendance link, I hope you have recorded your attendance in the Google form given. We will ensure that that goes into the attendance based on what data you have registered. And feedback link, we will be sharing it over mail and in WhatsApp, so ensure that you give your feedback without fail. And we will also share the recording of the session for those of you who would like to re-watch this entire session once again. And if any of you are interested to give a brief summary of what happened today in the next session beginning, I'll give you 2 to 3 minutes time. If any of you are interested, do message me. You're all connected in the WhatsApp group. You can message us and then we will, pick you up and we will talk to you and we will have you slotted for the next session, first 5 minutes basically. So, I mean, this is a good way to reflect on whatever you have learned. So with this, if there are no questions, I think thank you so much, Priyanka and Aishwarya. Nice of you. We will look forward for the next session by Ms. Kavya on Thursday. Thank you so much.
Thank you so much. Thank you for the
Yeah,
opportunity.
thank you. Thank you, SKK. Thank you, Ravi. Srihari, you can stop the
Thank you.
recording.
Thank you. Bye.
Bye. Thank you. So if there are any questions now, I will unmute allow you to unmute. You can